Hi, this is Mike Tochik, and I'll be doing a presentation on grounding mats and their use for step and touch voltage protection. Here's our topics for today. First, we want to talk about why we use grounding mats at all, and then how they function, and we really need to talk then about some of the performance differences which are pretty notable between grounding mat styles. There also are other topics about materials that are used in these mats, and we have to give thought to how we arrange them and what other objects or structures are nearby these mats so we don't miss the entire topic of overvoltage protection. The purpose of these mats is to provide worker safety because pipelines can be subject to AC faults and they can be subject to lightning. So we have to have mats in the vicinity of pipelines and other structures in order to provide voltage protection. So the mats are obviously a metallic construction of some type, and there's different ways to arrange these around the pipeline and structure. Overall, what we have to do is limit the step voltage and the touch voltage, or I'll use the word potential in the place of voltage sometimes, and we have to keep these values to safe levels for workers so that they don't have a shock hazard present at a work site. A step voltage or step potential is defined to be the voltage between a worker's feet when they're at a 1 meter separation and there's a voltage gradient in the soil. This is where a gradient control mat comes in, is to limit that to a safe level. It's a NACE standard and others that define what is that step potential. It might look like this graphically. Without touching anything, a worker has a voltage gradient experienced radially away from a structure, such as a pipeline, or it could be another structure, such as a transmission tower. But that voltage gradient in the earth could be excessive unless there's a grounding mat used. In contrast, a touch potential involves contact with a metallic structure. So when it comes to talk about grounding mats, it's assumed that the worker will be standing over a gradient control mat for his benefit when he's making contact with a pipeline. And this is also defined as a 1 meter separation as you're contacting a metallic structure. But practically speaking, touch potentials are really the voltage difference between any 2 points that you can get across. So an example could be an insulated joint that has a voltage difference on either side of it, or any 2 metallic objects would be another. And graphically, here's how this would look. Making contact with a structure, and then again, the purpose of the grounding mat is to provide protection so that the surface of the soil and the metallic structure are nearly at the same potential. There are guidelines and standards that relate to overvoltage and worker safety. That would be IEEE 80 for the AC power frequencies used, and there's an IEC standard for higher frequencies, such as would involve lightning. The purpose of the gradient control mat is to limit the voltage radially away from the pipeline in the earth. This would be a step voltage. Also to limit the voltage between the metallic structure and earth, as an example of a touch voltage. And we want to limit the voltage between any other contact points as well. And this has a lot to do with the arrangements and layouts of the mats or arrangement and layout of a facility. In terms of limiting voltage, some cases are more difficult than others. AC power frequencies are actually manageable and easy to control with a reasonable ground mat design and other practices. But when it comes to lightning, this is much more difficult, and there's many factors relating to lightning that are overlooked in grounding mat design and application and installation, and this results in very large overvoltage conditions that might not be known to the industry. Here's a graphical example of AC faults, or an AC fault current. So the blue line graphed here shows an AC fault with a duration of a little over 4 cycles before the fault is interrupted. So it's sinusoidal waveform, and it actually is relatively slow as compared to lightning. A lightning waveform, as seen here on lab equipment, in this example, a 100,000 amp peak value of lightning, is a relatively fast event. If you look at the time scale, you'll see that it's measured in tens of microseconds. So it's over rather quickly, and it's this very fast rise time that makes a difference as to how lightning acts different than AC faults. It's the steep slope of a lightning waveform that causes all the problems for worker protection and equipment protection. The rise time or slope of that waveform is exceedingly steep. It's on the order of 10 microseconds or so, roughly, for a rise time up to peak, and then a decay from the peak down to some lower value. The way we get potential differences and the voltage that we can experience in a pipeline setting, for example, is due to the current flow through that path producing a voltage drop. So the main factors involved for our topic today would be the voltage gradient that's across the mat, and that would relate to step voltage, and also what is the voltage drop in the wires that connect the pipeline to the mat. As we're going to point out, there's significant effects that come just from how we connect structures together with wires. The total voltage involved, where we tend to think of it in slang terms, that's an IR drop. It's a current flow through a resistance. Well, that is true, but there is another factor, and it's going to overshadow the first one, and that is an inductive effect, where the inductance of the conduction path, think of the wires and the gradient control mat, it will have a particular property called inductance. And also there's another factor that is the rate of change of current. And you could imagine from this waveform, if inductance were high, or if the rate of change of current were high, then you'd end up with a very large voltage. The IR component can be discussed for just a moment, and then we're going to dismiss that because its value is not that great compared to the other factor. For a typical conductor, such as a number 4 stranded copper conductor, its resistance is very low. So even for a reasonable peak value of lightning current, the total IR, or voltage drop, is really quite low. The more notable factor for a voltage drop relates to this LDIDT component. And the inductance L is determined by the design. We can control this because it has to do with conductor length or mat performance or design. The rate of change of current is not something that we can control. That's the lightning effect. Now I'm going to take a sidestep here to talk about materials for just a moment. There's common materials that are used, such as zinc ribbon or maybe a copper grid or copper wire. There's also materials that attempt to use steel but then clad them with something such as copper or galvanizing to provide corrosion protection. And there's different mat designs out there. Here we see grid style mats, spiral mats, or a zigzag arrangement, which is still a single wire system, just in a different shape than a spiral. Now we'll start to analyze the two major different styles of mats: single wire systems and gridded style systems. In a single conductor mat, if we were to look top down, we'd see a picture like this. Say a pipe coming out of the ground bonded to a spiral zinc ribbon or wire that has an ever-increasing radius as it forms a spiral. We're going to make it of a certain size, and then we're going to compare next to a grid style mat that has the same dimensions. You'll notice in this image that the current must flow on the single wire from the pipe outwards to flow on the mat. In contrast, a grid style mat, which for the purposes of comparison has been cut into a circle shape, but no one takes a grid style mat and actually does this, it would probably be rectangular or square material sheets. But it's been cut into this shape for comparison, and you'll see that the current flow is in all directions radially away from the pipe to which it's bonded. But it's going to be constructed to the same dimensions so we can compare the performance of the two mats. Now let's look at inductance values. Back to the single wire system, for the dimensions that I outlined in the first slide, there's a certain inductance to this mat. The first 1 foot turn from the center out 1 foot has a particular inductance value. It's stated in a unit called henries, and you'll see it's a value that's in this case about 10 to the minus 6 henries. And if you go out the next 1 foot increment, you'll see that that value has about tripled. So the inductance of a single wire system increases with the radial distance away from the center point. This makes sense because we're adding more and more conductor to make ever increasing distance and circumference around that point. Now let's do an inductance calculation on a grid style mat of a particular design, but to the same dimensions as the single wire system. You'll note that for the same first 1 foot distance away from the pipe coming out of the ground, there is an inductance value, but you'll note that this one is 10 to the minus 9th. So it's 1,000 times smaller than the single wire system. You'll also note that the next 1 foot increment is about half of the first increment. So here in this design, inductance is dropping with radial distance away from the pipe. And this is going to be a key differentiator between the two mat designs. Well, what type of rate of change of current might we have? We now know what inductance is, but what about the rate of change of current, this di/dt value? Well, there's various values that are used in industry, but the actual slope or rate of change can get extremely high for lightning strike. There's considered direct lightning strike values or even indirect lightning strike values that are a little bit lower, and these are derived through measurement. So you might wonder, well, how do you get these kinds of measurements? Let's show a picture of how this is done. This is a rocket-triggered lightning test where a rocket trailing a very thin copper wire is shot into the sky when there's high stress conditions, meaning basically storm clouds overhead that have not yet initiated a lightning strike, but it has a high enough potential that it can with a little bit of help. The purpose of these tests is to basically bring the ground potential right up to the level of the cloud so that lightning basically must strike it. And then they can instrument this and get all kinds of data such as rate of rise. So let's take a look. You'll note that there's multiple lightning strikes or multiple flashes in each frame. What happens is as lightning initiates, it ionizes the air and it makes a very conductive path, and there's multiple return strokes as well that can follow that very same path. And if this is instrumented, they can obtain quite a bit of data on this. So now back to our calculations. If we were to calculate the voltage that results from the inductance and the rate of rise of current, this is the value for a single wire system. We see values that are in the tens of thousands of volts. So we're looking at some enormous values. And recall that inductance increases with each 12-inch radial increment. Therefore, this value is going higher and higher. Can you even get values this high? Well, you really can't. If you had voltages that were in the tens of thousands of volts per turn, they would just be arcing between turn to turn in the soil. There's no way that the soil could withstand this kind of voltage. So practically speaking, this kind of a design is not going to afford protection in any way. If we look at a grid style mat, we started with a low inductance, so we end up with a low voltage. So it has the same rate of rise of current, the same lightning waveform has been applied to this mat. But because inductance is so low, now we're looking at a value in the tens of volts, not tens of kilovolts. And note that, as we learned before, inductance goes down with each 12-inch increase away from the center point from the pipe. So here the voltage is going to drop. If we were to compare the single wire system and the grid style mat and form a ratio, you'll see that even for the first foot away from the pipe on the mat, you have a ratio, a ridiculous ratio of almost 1,000 to 1. And that ratio is going to increase with each 12-foot increment away from the pipe. Let's look at a table of data for the single wire system. In the first column, we see the radial distance away from the center, and this is from the center of the pipe, which is why the first value starts out at 6 inches and then goes 12 inches from there. The second column shows the touch voltage, and you'll note these values are in kilovolts or thousands of volts. So the first foot is 48 kV, the next one is 150 kV roughly. You'll note also that the step voltage in the third column starts out at some notable values and then also increases. Now looking at a grid style mat for the same waveform and the same radial distance away from the center, you'll notice in the second column the touch voltage, which is in volts, not kilovolts, is merely in the tens of volts or maybe low 100 volt range. Now look at the third column. The step voltage is very low and it actually decreases as you go away from the pipe and towards the edge of the mat. So extremely good performance for both step and touch voltage. If we were to go back and show a ratio of grid style mat to single wire mat voltage ratios at every point on the mats away from the pipe, you'll see that these values get to just ridiculous levels. Thousands to 1 of ratio in the voltage performance. Now, what we've done in this analysis is assume that all the current is flowing through the mat. We also assume that the worker's standing directly on the metal of the mat and there's not another barrier to add. In reality, there's crushed high resistivity stone added on top of that mat. We also have made an assumption in the numbers I've shown that there's basically no wire connecting the mats, no length of wire, so that its inductance is 0. But that really is not true and must be taken into account because there must be some wire length to attach that mat to the pipe. And in fact, due to the inductance discussion that we've already had, you can see that increasing wire length adds inductance, which increases the voltage. So it has a strong effect on the resulting touch voltage. Interestingly, it doesn't play a part in the step voltage because, again, in the step voltage, you're not contacting any structures. It's just the distance in the soil between the 2 feet. So if we look at the performance of a wire and consider its inductance, there are typical values that a conductor may have. And if we added one 24-inch wire to connect the pipe to the mat and use the same rate of rise of current, then the resulting voltage is quite substantial. It's adding thousands of volts to any mat design. It does not matter what the mat design is in this story, because in this case, this example of 6,000 volts is strictly in the wire itself from the beginning to the end. So the message in all of this is to use the very shortest conductors that you could to attach a structure to the grounding mat. If you add multiple leads in parallel, that cuts the inductance in half. For a given lead, if another one is put in parallel, its inductance is halved. Now in reality, high resistivity stone is added on top of any mat design, some number of inches. The purpose is this reduces the current flow through the worker, and it even further separates a person from the effects of the mat. Whether the mat works well or poor, stone is an added benefit. And in some cases, for a single wire system, the only good part of that design whatsoever is merely the stone that's on top of the mat, because the mat itself is a very poor performer at voltage limitation. Other things that need to be thought about with mats. You do need to think about materials because of their longevity in the soil or any kind of galvanic interaction. Whether those mats are directly bonded or whether they need to be decoupled, where a decoupler is that solid-state AC conduction DC isolation device that can allow things to be safely bonded but not have a galvanic corrosion cell produced. So again, a decoupler. Also, we need to think about, do we have to bond to other nearby structures? In some cases, other objects are so close that you must bond to them for safety because you clearly could be touching them while you're contacting another object or while you're standing on the mat. And they must be referenced to each other. But the thought is, should you bond or not? And finally, we need to think about, well, what different arrangements exist in facilities? How might you arrange the mats? First, on materials. If a material is compatible with another object, it could be bonded together. So for example, a galvanized mat could be bonded to a galvanized fence. If we were to bond dissimilar systems or bond to a CP system, that cathodic protection system will also attempt to protect the mat. But even if there is no CP system, you could be creating a galvanic corrosion cell by bonding the mat with its material to a pipe or the mat to some other thing like a fence or a support structure for a pipe or another object. So in that case, cathodic protection, or really galvanic corrosion current, will be exchanged between the mat and that other object. But we want the mat to have a long life, so we have to consider what we're bonding to. Decoupling can be very useful with gradient control mats because the bond from the mat to the other object will have no effect on cathodic protection and will not create a galvanic corrosion cell, but it will be a fault-rated, lightning-rated safety bond. So that makes the choice of material for the mat become irrelevant if it's bonded because it's not going to create that corrosion cell. That does mean that you can use less costly materials, and it means that there won't be an effect on the CP system. Now, regarding bonding to other nearby structures, other objects could be at a totally different voltage, a different potential during an AC fault or a lightning strike. You could picture a gradient control mat near a fence, but not bonded to the fence. If you were to touch that fence during the event, there could be a very large voltage difference across you. So you must determine if direct bonding to that nearby structure is appropriate, and that has to do with materials and whether or not there's a cathodic protection system involved, or if decoupling to make that connection is most appropriate. If you're in doubt, decoupling will eliminate either of those issues, whether it's a CP system or just a galvanic potential difference. It makes a safety bond without a corrosion cell. The arrangements of mats are typically out to about a 4-foot distance away from a structure such as a pipeline. The reason is that's about as far away as you could be and still contact the structure, and yet you'd be standing over the mat. You do have to think about whether that distance out to 4 feet now puts the mat in close proximity to other structures. The other thing to think about is if you have a facility that has gates, as someone walks up to that gate and makes contact to, say, unlock and open it, they clearly are touching the metallic fence. Consider if mats should be used for that approach, both inside and outside the gate. The answer is they probably should be because there is exposure for workers at that point. Here we have an example of a test station. The test station is shown with a bird's eye view coming out of the ground, or this could be a pipeline coming out of the ground here, with an 8-foot by 8-foot mat surrounding the object. This gives us about our 4-foot protection away from the object. And this would be a typical arrangement around a test station, especially those in a high power line corridor. Let's go to a different site. Let's imagine that there's a motor-operated block valve site which just needs a small enclosure, small fenced-in area for a pipe coming out of the ground, the operator, and then back into the ground. So we have, again, a very confined area. What might come to mind about this arrangement? Well, we'll add ground mat around the structure, and I haven't shown it throughout the whole facility, but you'd put it inside the fence. And it's in very close proximity to the fence. And we did want to consider the gate approach as well. But there's one more thing we need to look at. We now need to add decouplers to reference the pipe at each end of its run to the ground mat, and we need to reference the ground mat to the fence. If we don't want to create a galvanic corrosion cell between the mats and the fence, then the decouplers are useful. Let's look at an even larger facility. I've just drawn in a single section of pipe in a presumed large facility, and I just put in some nominal dimensions there. Let's just say that this pipe is nowhere near the fence, but there's quite a bit of piping within the facility. Well, we would use the principle of having the mat follow the pipe out to a 4-foot distance wherever that pipe goes through the facility so that there's worker protection. So we've accomplished that in installing the mat in this scene. However, what we haven't done is reference the mat to the pipe. So that's done via decouplers, and then the cathodic protection of the pipe does not interact with the mat. The mat, in other words, does not look like an additional load on the cathodic protection system because the decouplers make it look like it's not even connected from a DC standpoint, but for AC and lightning effects, the pipe and the mat look like they're bonded together. So for AC fault exposure, both single conductor mat systems and grid style mats likely provide overvoltage protection for those faults. But when it comes to lightning, there's a large differentiation between mat styles. The grid style mat will provide very good step voltage protection, and it can also provide very good touch voltage protection as long as it's connected to the structure with very short wires. That same comment applies to any mat arrangement, the wires that connect it. But a single wire mat system cannot provide protection for lightning due to its inductive effects. We want to apply mats out for a distance of about 4 feet away from structures to assure that anyone that could possibly make contact with the pipe would be standing on that mat. Mats have high resistivity fill added to even further limit the effects on the person by limiting the current flow through their body. And you want to look at and consider if bond wires or decouplers are needed for other nearby structures so that those structures remain referenced to each other if they could be simultaneously contacted. We don't want structures at one potential and you standing at a different potential. If this spurs questions, feel free to contact me. I can be reached at dairyland.com, and I'm glad to provide this information on grounding mats.